right, let's go ahead and start the recording and start the lab. Yeah, pretty much that's it. So what we're going to do first is we're going to import the data set that we're going to be working with for the lab, for the demo, through our sklearn library. So sklearn or scikit-learn, that's the library we're going to primarily use to implement all of our stuff during this weekend. And there are other kind of libraries that you can use, PyTorch, Keras, etc. But scikit-learn is kind of the best documented and the simplest to use, so we're going to go ahead and use that. So when we import the data set, I'm going to sadly get rid of the hello world. We're going to do from sklearn .datasets import this specific function. So this function is called the load iris function, and what it does is it loads the data set that we're going to use called the iris data set. Okay, so instead of having to, download the data set, upload it to Google Colab, or like mount your drive or something, you can just use this function. And in order to actually load the data set into variables, we're going to do the following. So we're going to do x, y equals load iris. That's how you type. Then return x, y equals true. Okay. And that just gets the input features and the output and the labels. Thank you. Gets the input features and the labels into the x and y variables. Okay, and commonly x is used to represent inputs and y is used to represent outputs or labels. There is a convention that you use capital X, but for this it doesn't matter. We're just going to use lowercase x. The reason we use capital X is because it's usually a matrix, and capital letters for matrices. Okay. So now that we have our actual data set, we can kind of inspect it a little more. So we're going to combine the data set into just one 2D list for now, so we can inspect the data in more detail. And for today, we're just going to stay with 2D lists. Once we get into like pandas and data manipulation tomorrow, we can go ahead and do that. Yes.
Do you need to have the number like in front of?
Oh, that's just a line number. So that's just automatically put in every time. I can turn it off if it's confusing.
Probably easier for you to go on page.
Oh, sorry.
Probably easier for you to identify lines and code that way.
That's true. Just know that, okay, just know that the one in front is never like, you wouldn't write 1xy, right? So that's not part of the code, that's just a line number, okay? So we're gonna go ahead and do the following. So we're gonna create this list, and then we're just gonna loop through everything. That's awesome. Okay. And then please let me know if I'm going too fast or if I should, yeah, I mean, if I should slow down. The Zoom I know is kind of laggy, as is my computer, so. Okay.
Your control also makes the
Yeah. That's better. And make sure you make the sample, so each line a list, because for now arrays are kind of, we're just not going to use arrays because it's a little difficult to manage. Okay, so now that we have our data, is everyone there? Right, we have all of our data. We can go ahead and type in data 0 and grab the first row of our data, and I'll tell you what the each of these columns represents. So the columns represent, in order, I think, sepal length, sepal width, petal length, and then petal width, right? But at the same time, my computer's being really slow. No, at the same time, just one more time here. We should have a fit data set, but the function is a little broken. This is also a good lesson in I guess debugging. So what should happen is that we should have a like a 5D list. But yeah, so that's all of our data. I don't know why things are broken. I think it's because there are multiple people maybe on the same collab, but essentially, what we want to do is we can confirm this by looking at yeah. So the y variable should be kind of our output classes. So 0, 1, or 2 are the different they represent the different classes of flowers. Yes. Not that. Okay. Okay, let's go over this code box again because it's a lot. So essentially what we're doing is we're making this 2D list of data. Now it has 5 columns, which is good, but we're going to loop through all of our x and y variables from our load iris function, and we're going to append them to this sample list. And we need to make sure that we cast our x's to a list because they're actually stored as arrays. But once we do that, we can go ahead and append this list to our big data list and get our data set. So what we want is this 5 column 150 row 2D list that has all of our data in it. And as you can see, in the last column, which is our outputs, we have 3 possible outputs. Okay. So given that we have 3 distinct outputs, 0, 1, and 2, which represent the different types of flowers, they're called Setosa, Versicolor, and Virginica for anyone that's curious. Given that we have these discrete outputs, however, what type of algorithm should we use? So which one of the 3 algorithms do we want to use? Does anyone have a guess? Yeah, so we want to use a classification algorithm.
Oh.
Yeah, out of the 3. Yes. Yes, exactly. So we want to use logistic regression. And for future reference, don't worry if you're unsure of your answer, just speak up loudly like I'm doing, okay? Yes, exactly. Good. Great. And that just make sure everyone can hear you, okay? So that given that you will most likely say the correct answer, I have confidence. Everyone can hear you, okay? So we do want to use logistic regression. In order to build a good logistic regression model, we're going to reserve a small subset of the data for testing. And this is building something called a train test split. This is something that we'll discuss a bit more as we get further into optimizing and evaluating machine learning algorithms. But for now, all we need to know is that we're going to quickly shuffle the data set to make sure there's no like stratifications, like all zeros first, then all ones, then all twos. So we're going to shuffle it, and then we're going to split it up. So before I give you the shuffle code, make sure you only run the shuffle code once. Because if you run it different times, if you run it like say 2 times or 3 times, it might shuffle differently compared to what I have here. And even by default, if you're on a different operating system, so a Mac, for example, it might also shuffle differently. But just make sure that you only run the shuffle code once.
So
Yes.
something is not randomized then?
In this case, the way we're doing it is we're setting the seed. And we're using like random.seed0 and then random.shuffle from Python. So we're setting the seed, so it's not randomized, but it's pseudo-random still, which is good enough for us. Okay, so import random.seed0, and then random.shuffle our data set. Okay, so now that I've run it once, I'm not touching that code cell ever again, unless I rerun everything else before it, which is, it's kind of a pain. Okay, so now that we've done that, let's make sure it's actually shuffled. So let's scroll to the top. Scroll to the top. All right. So you can see it's going to start with 5.2, then 7.0, then 5.5 in the leftmost column. Okay. So once everyone's done that, make sure to confirm. I'm not sure if your shuffle will be the exact same, but just make sure that you run the shuffle code exactly once. Okay, not more than that. In the meantime, I'm going to plug it in. Is this output?
That should be plugged into the wire.
All right. Has everyone shuffled their data exactly once? Yes? We all good with shuffling? Okay. We can continue. Okay. So one of the reasons we actually combined the input and output earlier is so that everything shuffles together. So all of the inputs and all of the outputs are matched, from the beginning. So like, for example, we wouldn't have an input of 1 that is corresponded to an output of 0, okay? So now that we've done that, we can go ahead and separate the shuffled data into input and output again. So let's make our X and Y. And then for each line, we're just going to go ahead and yoink the corresponding data. Okay, there we go. You can go ahead and run that. And I'm going to, everything is saved to the notebook. So if you're still on it, you should be able to see it. Okay. So now that we have all of our data kind of set, we can build our logistic regression classifiers. Okay. So does anyone, given that we have 3 classes, we kind of need to use a multi-class classification, right? Does everyone see why that is? Yes, okay. So does anyone remember either of the specific multi-class classifiers that we talked about? There were 2. If that jogs your memory. Yes. Yes, so 1 versus 1, and then 1 versus all, or 1 versus rest. There are a lot of names of, but yes. So those 2, we're not actually concerned with which one we use, given the way we implement this, but those are the 2 that essentially we'll want to use. So the way most actually AI applications are built is that they take a pre-built model from a library, and then they fit that model onto your data set. Because of the way that that AI models are created. So a lot of them require a lot of making the model and making the math behind it more efficient. So we're not concerned with that. We just want to use our model. So we're just going to take a logistic regression from sklearn. So from sklearn.linear model, import logistic regression, and then call it something like logreg equals an instance of this logistic regression. Okay. So now that we have that, we're going to go ahead and build our test train split as we talked about before. So we're going to do that like so. We're just going to have test x equals the last 10 elements, test y equals the last 10 elements, and then the training set is all of the rest of the data. Okay. Okay. And then once everyone has their train test split, just kind of look up, up here that you're set. Yeah. All right. So now that we've built our train test split, is everyone at that point? Okay, good. So we can go ahead and fit our model. So we can do log reg equals log reg dot fit on our training data. Okay, so on train X and train Y. And what this does is it modifies the weights that we talked about with the logistic regression model, and it builds or it, I guess, changes these weights in order to best fit train X and train Y. Okay, so now it's fit. Let's go ahead and run all of these code cells that I haven't run. Okay, and then once everyone has run that code cell, okay, you should receive this kind of weird, a little bit scary warning or error. It's not an error, I'll tell you that, but it is something that we should fix. So once you're there, kind of talk it out, think about what you might do to fix this warning. And I'm gonna want all of our like specific groups, or one person at the group, if you're one person at the group, to shout out one idea at the end of what we should do to fix this error. Okay, so once everyone's at this point, please discuss.
This Wi-Fi, this Wi-Fi might.
Yeah.
Yeah. Well, yeah.
Oh, and
Yeah.
yes.
You guys see it?
The two lines that are trying to make didn't meet within the iteration that are not.
What do you do?
I think this one.
I feel like if it like reached like a stable logistic function.
Yeah.
Yeah, getting out of that.
Something saying that we're expecting it to be alright, but we got a one year. Yeah.
So right now, we start importing the data. So you combine it all into one data set to make something operational later.
Right. Here, we're not. Here, we're gonna shove more data, random, not just send like all zeros and all ones. And so that's what we do. What we do is we pull it from we pull a previous model from scale. Yeah. And then we use that model onto our data set. It's and then we use that model to match. First, this error, or this is not an error, it's a warning. This warning represents something, and it's your job to figure out what it is, how potentially you fix it. So, all right. What does everyone think is the best way to fix this issue? So, convergence warning, LBFGS, failed. I can keep scrolling. Failed to converge, status equals 1, stop. Total number of iterations reach a limit, increase the number of iterations, max underscore ITR, or scale the data as shown in this. Please also refer to the documentation for alternative server options that. Okay, so what does everyone think is the problem? Let's go start from here, and then we can go in a circle that way and circle around. Okay, so please. What do we think is the problem here?
But I guess like we talked about the total number of iterations we've reached, so maybe trying to fit the model on the data. I'm not sure like how this is happening like in the mathematics, but every time the model's being fit on the data, there's a new iteration.
Okay, interesting idea.
Yeah, so we looked at the documentation.
Oh, wait, hang on. Can you say it again?
We pulled up the documentation.
Hold up the documentation. Here you go. Everyone should, I mean, if you're curious, you should have clicked on the links, right? But it's always a good idea when you're not sure what happened to go to the documentation. I'm sure this was touched on in like in Python and various CS classes, right? Always go to the documentation. It's no different in AI. Okay, sorry. Continue, please.
So max iterations, or that max iter is a value that you can set when you're setting up a logistic regression model. So you can raise that max iterations and allow the model to run longer. But then also, I'm not sure if the data needs to be scaled for a logistic regression model, but I think that helps to decrease the number of iterations it takes to train the model and scale your data, because it kind of like standardizes the step.
Okay. At the very back table here, not Nate and Pete. What did you think was the issue with the warning? How do you think we should fix the warning? That's okay. That's why we start from the documentation. Okay. Very often in AI, you're going to be faced with that, which is like you have some sort of random message that you have no idea how to get. Okay. So Absolutely very valid. Please.
Yeah, so the pair of states needs to increase for the maximum integration reach. So, intuitively you think that you increase it to that integration.
Absolutely. Please. Similar ideas about the max underscore ITR, increasing number of max iterations, okay. Here. Similar as well. Yep, similar as well. Okay, so there's a lot of increasing the number of max iterations. Okay, we heard a little bit of scaling data for logistic regression and this parameter called max underscore ITR. Okay, so that was referenced both in the documentation and also, or not in the doc, in the warning message and also by this table here. Okay, so when I pulled up the documentation on screen, so everyone please redirect your attentions to our screens. You can see when we zoom in here, max underscore ITER. It's an integer and its default is 100. So the maximum number of iterations taken for the solvers to converge. So in order to increase the number of iterations like everyone has said, what we're going to do is we're going to go, hang on, back up here, and we're going to add max underscore ITR equals, someone shouted a number bigger than 100. First number, right?
101.
101, 1000. Okay, 100, 1000. No, I'm kidding. We shouldn't do that. Let's go with 1000. If you go too high, it's going to take way too long. Okay, so let's just stick with 1000. And the reason I didn't pick 101 is because adding one iteration generally doesn't solve the problem. It can. And if you're, I guess, lacking on computational resources, it's always a good try. But for now, we're going to go with 1000. And you can see it ran without error. We're all good. Great. Okay. So that illustrates one principle that I'm sure has been commonly talked about in CS, but is also very pertinent in AI. When you're building an AI application, always refer to the documentation of whatever, library you're using. And that's one of the reasons why sklearn is kind of the library we choose to use, because it's well documented and a functional library. Okay. So now that we've fixed this issue, we can go ahead and actually predict on our testing samples. So we'll go ahead and write predicted y equals logreg.predict on the test set. Okay, and when we run that, we can go ahead and see what predicted y entails. And the answer is this array of numbers. Okay. And then when we look at the what's it called? The test comparison, we can see that only number 3 was incorrect. So predicted y predicted 2, or our predictions predicted 2, whereas the answer was 1. Okay, and 90% accuracy is a very, very good start. Okay, so great job. You've built your first AI model. Congratulations, everyone. Okay, but we don't have to stop there. We can continue. Okay, so another thing we can do is we can predict a specific feature from the other 3. So for example, we can predict pedal width from all of the other features. Okay, so given that this is now a continuous kind of real numbered value, what type of model do you think we should use? Anyone? Yes, please.
Polynomial regression.
Polynomial regression works, and linear regression also works, because realistically, they're both effectively the same thing. So we're going to start with linear regression. Polynomial regression is going to actually be a bonus task when we assign you your kind of work or classwork to do, we'll say, in the lab. But let's start with linear regression. So we can go ahead from sklearn.linear model import linear regression. And then we instantiate it in the exact same way we did with logistic regression. Okay. And now we need to kind of build new train test x's and y's, because what we want to do is we want to predict the 4th column from the first 3. So we can't use the same data set that we just predicted on, because it kind of has the answers already incorporated in the x. So what we're going to do is we're going to do something like this. Okay, so new train x equals empty, and same thing for new train y. And then for line and train X, we're just going to append everything except the last value, so the first three columns, and then we're gonna make the output the label, the last column. And then same thing for test X and test Y. Okay. So I'm gonna upload these two. And you can see, if we look at, for example, new test X, you can see it's only the first three columns of our test data set. Once you're done with this, you can go ahead and actually use the exact same .fit command on your training data set. And this time it runs without error because it does. We've already discussed that. And we can also make predictions as well. So let's go ahead and do that. And not forget a parentheses. Okay, so it should look something like this. Okay, once everyone gets to the predictions it's made, I'm not exactly sure if it'll say the same values, but you should have a list or array of 10 predicted values that you've been given. Everyone, make sure when you're predicting, you only get 10 values and not like 10 times 3 values. Okay, so make sure all your colons are in the right places or lack thereof. And make sure you type essentially everything exactly as it is on the screen and make sure you get the right outputs. If you don't get the right outputs, you can have practice debugging. Okay.
So while we're kind of going along and like getting towards predicting, maybe if you've already finished with the predictions, can anyone tell me what is kind of the next step when we build an AI model? So we've built a model, okay, it's predicting, now what? It's the second step. Yes, please. Evaluate the cost function, right, exactly. So let's do that. Okay, so as you can see, these are our 3 steps. It's for polynomial regression, the principle's the same. Build a regression model, done. Now we need to evaluate the cost function. All right. How do we do that? Well, let's go back to our code. Here we go. And let's see. So if you go on the documentation, which is not necessary in this case, but if you do, you'll find that there's this function called score. So you can do something like this. So linreg.score, new test x and new test y. And what that does is it compares the predicted values here with the actual test values that you give it, and it gives you an R² score. So here we can see that approximately 81% of the variation in our data can be represented by our line of best fit. So our data set is like 81% linear, or it's like our prediction model is 81% accurate. Okay, which is pretty good. So now that we've done that, I'm going to go ahead and post the